Okay, so this is Physics 2211 Lab 3 by Yu Chen. So in this lab, we recreated an orbit of a star around a black hole, and we were all assigned trajectories based on our GT emails, and we wrote glow script code to model the trajectory and calculate the net forces acting on the star at different points in the trajectory. So the main concept in this lab is Newton's law in terms of a curving motion, parallel direction. It's the formula is F net equals dl pl over dt times p hat. The F net in the perpendicular direction is LPL d p hat divided by dt, and you just add them for the combined. So uh, in the glue script code, this is all given. So I'll just scroll down to the stuff that we had to edit. So we have view constants where, you know, the gravitational constant is 6.7 e to the negative 11. There's the mass of a star, just 2 e to the 30th. Time interval between important data points is 86,400. Yeah. So the V initial is this is the V final. The P initial, the P final, and obviously for delta V, just take the final and subtract by initial. Same with delta P, P final minus P initial. And then we need to calculate dp dt, which is just delta P divided by delta T. And then use Newton's cycle law to calculate F net, which is just F net equals dp dt. Then we calculate dp divided by dt in the parallel direction. And then we calculate F net par, dp dt in perpendicular direction. Same thing. And here we calculate the mass of the black hole, which is R equals or position of the origin minus position of the star. Yeah, MPH. And then, yeah, we just change all this to the corresponding values. And if we run it, just gotta give it a second. Yeah, just take a minute. That's strange. Oh, there we go. Yeah, as you can see, models the orbits around a black hole. So what does it mean? A net force can be decomposed into parallel and perpendicular components relative to a star's velocity vector. The parallel components affect the speed of the star, either accelerating or decelerating along its trajectory. The perpendicular component affects the direction of the star's motion, causing it to change its path without altering its speed. And also the rate of change of momentum. So similarly, the rate of change of the momentum can be decomposed into parallel and perpendicular components. The parallel component represents how the star's momentum changes along its trajectory, affecting its speed. The perpendicular component represents how the direction of the star's momentum changes, influencing its path but not its speed. And what if, to enter around the black hole, the spaceship's initial velocity must carefully balance gravitational pull with centrifugal force? This balance, crucial for avoiding collisions and maintaining stability, depends on factors like black hole mass distance and desired orbit shape. Calculating this precise velocity involves complex equations considering gravitational forces, often requiring iterative calculations or advanced simulations to ensure its stable trajectory, especially near the black hole's strong gravitational field. And that's it. Thank you for listening.